Alright, hey everybody, let's do I guess it's day 4. I'm going to try to go a little quickly here. I got a son who's napping. When he wakes up I got to take care of him, so let's see if we can do it while he's asleep. So like we said, this day 4 is a lot like day 3. You're still just graphing these functions. They're going to be a little more complicated in day 4, and there's going to be more of a focus on giving the function properties, but it shouldn't be bad. So with that said, your first step should still be just to factor everything. So we've got the x plus 3 in the numerator. The denominator factors to an x minus 5 and an x plus 2. So right away, I see that nothing cancels, so we have vertical asymptotes but no holes. I also see that we're back to a denominator that has the greater degree. So we're back to having a horizontal asymptote. That's at y equals 0, and we don't have a slant asymptote. We're leaving those, we're not leaving them behind, but everything is mixed together again. Day 3 was all slant asymptotes, but now everything's a big mix, and you have to think it through as to what kind of asymptote you have. But we're going to have vertical asymptotes that are at x equals 5 and 1 at x equals negative 2. That means our domain is all reals except for those two values, 5 or negative 2 and 5. You are supposed to go in numerical order as you list restrictions. So what just happened? Nothing happened. Right? Yeah, okay. My computer went weird, but we're okay. Write it in factored form. I already did that over here. Our x-intercept is still the 0 of the numerator, so that'll be negative 3, 0. And our y-intercept is still what we get when we plug in 0. So f of 0 is going to give us 3 in the numerator, negative 10 in the denominator. So it'll be 0, comma, negative 3/10. Does the function intersect the horizontal asymptote? Yes, we know that it does, because the horizontal asymptote is at 0, and we just said that we'll equal 0 at negative 3. That'll be our x-intercept, so yes, it's going to cross. Yes. If so, where? We already did the math. It's negative 3, 0. I suppose if you were going to show math, then this is where we would take the whole function and set it equal to the horizontal asymptote, so it would set it equal to 0. Cross multiplying, you get that whole thing to cancel. You get x plus 3 equals 0, you subtract 3, and there's your negative 3, right? Now the good thing about this method of taking the whole function and setting it equal to your horizontal asymptote, that works whether the horizontal asymptote is at 0 or whether we have a horizontal asymptote that's somewhere else, like when the degrees are the same and we're looking at the leading coefficients. If we had an asymptote at 4, we could set it equal to 4. If our asymptote was at negative 2, we could set it equal to negative 2. Something that I may not have said to both periods, although I know I said it to one or the other. If we had a slant asymptote, whose equation was y equals x plus 4, then we could take an approach where we take the whole function and set it equal to the x plus 4. And again, solve by cross multiplication. Now you can see where that would be a pain in the butt. You'd have to multiply your denominator by the x plus 4. You'd have to be distributing terms all over the place. It gets ugly. I definitely would prefer to have you guys just finding points of intersection with the slant asymptote by just doing the whole remainder over divisor equals 0 thing. Since that's safe and since that always works, I would do that. That's definitely simpler than setting the whole function equal to the equation of the slant asymptote. But this is what I would do for horizontal asymptotes. Hopefully that's clear. Now, I don't know what, let's just graph all the stuff we have. We've got a vertical asymptote at 5, 3, 4, 5 right here. We've got negative 2 right here. Horizontal asymptote is at 0. Close enough. Then we've got an x-intercept at negative 3. So right there. We've got a y-intercept at negative 3/10, so that's about a third. So like here, whatever, that looks more like a half, but that's okay. And we have no other points to plot, right? So what? So it is unclear as to whether I'm going to be above the asymptote and then coming down, or whether I'm going to be below the asymptote and then going up. So we better run a test point. And again, all we really need to do is check signs. I'm going to check -6, because who cares? But at x equals -6, if I plug that in, then my numerator will be negative. The x minus 5 factor will be negative. The x plus 2 factor will be negative. And I'm pretty sure 3 negatives make a negative. So I know that at 6 we're under the asymptote. So I can rest assured that our branch is going to be asymptotic from below. And it's going to kind of dip down and then come up, 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 and follow this thing up and out forever. So that's that branch, and I'm happy with it. There's no other place where we cross the x-axis. The only place where we crossed was here at -3. So the fact that my y-intercept is below the asymptote tells me that the entire branch has to be below the asymptote. It's going to pass through here, and then probably come down a little harder over on this side than the other side. Again, these things are not going to be symmetrical. My feeling is, with this point as close to the asymptote as it is, we're going to be kind of pulled to that side. You do want to do your best to maybe indicate that asymmetry. If you can puzzle your way through it, don't just draw the thing perfectly symmetrical. That would tell me that you don't know what you're doing. Alright, what's happening over here? There's no more intercepts, so we have a branch that's either fully above or fully below. And we could just run a test point to figure that out. Let's test the point, I don't care, 9. I like to use the numbers that are actually printed on the paper. So how's about 9? Well, again, all I got to do is check for positiveness or negativeness. So checking 9 gives me 12, which is positive, gives me 4, which is positive, gives me 11, which is positive. So for sure, we're positive. So that tells me that our branch is going to be fully above, coming down, 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 turning, and going out. So there's your graph. Now, I think I made a slight mistake with this. I was hoping, yeah. Alright, everything I drew outside of this grid is not going to stay stuck to this grid now. That's my bad. I'll deal with that later. So I think this was easy, right? I mean, you guys can come up with all these properties. We've been doing that since day one, honestly. So the only thing now is, let me grab this entire function. I'll just take a picture of it since I can't move it. Clipboard. And we'll go to the next few problems. Now this says that you now may use your calculator, but again, that's not quite true, because when the quiz rolls around, instead of letting you use your calculator, I'm just going to mark the important points. We're going to call them the key points. Maybe we'll call them the critical points. Maybe I'll just call them the extrema. But anyway, if you wanted these points, you would go to Desmos. So I'm going to pull up Desmos just to show you guys how to do it, in case somehow you don't know. But man, you should probably know. And then I got to add that. Does this even work? This should work, right? Windows CAPTCHA. Okay. Yes, that one. Okay. Sure. Right? No, don't like that. Yeah. Sure. Yoink. Okay. I think I should be recording that internet screen now. So if we go to Graphing Calculator, and if we plug in the function, which is x plus 3 over blah blah blah, x squared plus some stuff, minus 3x minus 10. Then we can see our graph. And as you can see, I didn't lie to you. We can see that this part in the middle, that concave down bit, it does have its symmetry skewed to the left, like I thought. We do see this point of intersection. Now we can just zoom way in on that to see that it's at -3, but another trick for finding the point of intersection is to just plug in the equation of the horizontal asymptote, like y equals 0, right? And now you can see it. And so now if you zoom in, that's my parents calling me, not picking up. Yeah, you can click on it. and it'll show you in gray that point of intersection. So if this point wasn't so obviously the integer value -3, then you could plug the other equation in and just find the point of intersection, which is a good plan. What else can we see too? If we scroll over a bit, oh, I clicked on the blue function, so let's click on the red, because when you click on the red, you'll see the point of intersection, and somewhere here we should see a minimum value. We might have to scroll pretty far to the left to see it, but it'll be there. No, it's not showing it. Why not? There it is, right there. So that extrema, that's a point that I'll be giving you. So it's -583. And the y value was -0.068. -0.068. So you'll have that. And then I guess there's one more extrema, which would be, well, way back over here. Notice it is not the y-intercept. The y-intercept is just a smidgen lower. There's our actual max. So -0.172. And -0. I guess 0.30. And so that's not exact, that has some round off, but whatever. Okay, so take me back. Let me just make, what window is this? Make it invisible. Boop. I did that wrong. Invisible, there we go. Okay, back to me. And let me grab those points. Shrink. So yeah, you can see those now. So now that you have those would help you shape your graph. Hopefully you would understand that -5.83, if that's over here, then that's telling you that that's the low point where our graph has dipped under the asymptote. Now it's dipped as low as it's ever going to go, and now it's starting to approach the asymptote again. So that point is relevant as we try to answer questions about increasing and decreasing intervals, right? We need that point. So we can plot that. It's going to be almost at the -6. So there's that minimum value. The coordinates are here, so I'm not going to rewrite them. But we also have, and my graph is obviously not quite right, because my graph is showing that the max is to the right of the y-intercept, and Desmos showed us that that's wrong. I wouldn't go nuts trying to fix that though, I guess. I don't want it to get messy, but we should actually be higher over here. So we should be coming way up, 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 then we're coming down and out. I guess I am going to go nuts trying to fix that, but white this out. Maybe bring white out to your quiz. White out, white out, white out, white out, white out. There, that's kind of over exaggerated, but I don't care. So there's another max right here now. We know that point is a max too. This guy doesn't have maxes or mins, so that's fine. But again, when it comes time to give the properties, I'll name for you some key points that you can label on your graph, and you can use them to answer questions. Now for this, I guess this is actually a little tricky, because when it comes to the range, do these graphs overlap each other or not? Have I just drawn it poorly? I don't know. Let's see. It says here that this point is only at a height of -0.30. So that comes up to, here. Now the other guy has its minimum at -0.068. So that is higher than the other one. So there is a little gap here, right, of values that will not be in our range. So your range needs to be -infinity up to the local max here, the -0.30. And then you can do the union of that with the local min up to infinity, so -0.068. Up to infinity. So that right away was kind of confusing. But hopefully you can handle that. Again, my graph is bad, again, because it's looking like these things overlap, but they don't. We should probably go back to Desmos and I'll show you more clearly. So you're still looking at my face. Let me turn that back on. There you go. So with us zoomed in the y-axis, you'll be able to see, you can see better now that there's definitely space between there and there. I can actually drag the horizontal asymptote to show you a little more what I mean. But look in here, can I change the step? Yeah, we're going to step by 0.01. So now we should be getting finer movement. Not fine enough. Alright, anyway, this is what I'm talking about. We know we've got that max like right here, and the other min is up here, and you can see that there is a little bit of space between there. That's what I'm talking about. So where is that? Yeah, so there's that point versus that point. There's a little bit of a gap between there and there, and we don't get those points over here either. Obviously, our branch stays above, so there's this tiny window of y values that our function never maps onto. That means they can't be in our range, and they're not. I took them out. See, I took them out. So yeah, you'd need to be able to do that too. Okay, moving on. What's our local or relative maximum? Well, handed it to you. It's right here. Again, don't be weirded out by the fact that the maximum has an overall smaller value than the minimum. Remember, it's local. Locally, this point is a max, so it's y equals 0.30. You could just say negative 0.30. And our relative minima is over here. It is at 0.068. Alright, so now our increasing intervals. So this first branch is definitely decreasing. So that's going to be negative infinity to the x coordinate of this critical point, which is the negative 5.83. Then after that, we are increasing to the asymptote, increasing again till we get to this max, then we're decreasing. So I now want to go from the other value, negative 0.17. That's a terrible one, but I'm not fixing it. And we're going to decrease all the way up to the next asymptote at 5. Then because there's an asymptote at 5, you do have to split the interval and start again from 5. And just say that you decrease from then on all the way to infinity. So we've got 3 decreasing intervals. And we're going to have 2 increasing intervals. And they're just going to be all the stuff between these. So we kind of know that we're going to start from this min and stop at the asymptote. So we'll start at the negative 5.83. And we'll increase until we get to y equals negative 2, or x equals negative 2. Then we'll increase again on the other side of negative 2 until we get to this local max, which was at negative 0.17. And that's it. So that's those. And then the limit stuff should be a piece of cake, I hope. As we run to the left, you can just follow the function. And of course we end up, moving along our horizontal asymptote at 0. So the limit is 0. As we run to the right, the graph is doing all this wild stuff, but as x's get significantly large, you're just going to be on this branch, and you're going to tend towards 0 again. So these are your end behavior limits. So all you have to do is follow your end behavior asymptote, either your horizontal asymptote or your slant asymptote, whichever one you've got. Now these are just the limits on either side of your vertical asymptote. So looking at negative 2, as we approach from the left, we're going up to infinity. As we approach from the right, we're going down to negative infinity. And looking at 5, as we approach from the left, we're going down to negative infinity. And as we approach from the right, we're going up to positive infinity. So that's everything. Is there anything I'm forgetting? Domain and range, increase, decreasing, extrema, some limits. I think that's it. So once you've got the graph, which we've really talked about a bunch, we've talked a lot about how to generate these graphs in the first place. Once you've got them, I think that next step of giving the properties is not something that should feel too difficult. Then again, it's now been 19.5 minutes, and we're only finishing number 1. So maybe I lied. I was explaining a lot. I was trying to give you a lot of background and stuff as we did number 1, because I figure anyone who watches this video is going to watch number 1, and then maybe you'll just tune out. So let's make sure number 1 is filled with as much exposition as possible. I'll try to do number 2 really fast now and see how many of you stick around. Alright, So looking at this, I see a cubic over a quadratic. I see that the cubic has all four of its terms. That's different. All the examples we did from the last one, there was no constant term at the end, and so they all had x as a common factor, and you could just factor the x out, and that made factoring a cubic easy. But since this does have a constant, the only other option you guys know at this time for factoring a cubic is to try factoring by grouping, and that's not going to work. So what the hell? Well, now I feel bad. Okay, what do we do? Alright, well, let's just say you won't get this on your quiz because I haven't taught you how to handle this. I'll teach you how to handle it now at home from your house, and you can probably guess it's go to Desmos. So off we go to Desmos. So let me turn that back on. Boop, here's Desmos again. Yoink. What you could do is graph the cubic and just look for the points of intersection, because the points of intersection are the zeros. The zeros give you the factors. So what was this silly old thing again? I believe it was a 2x cubed. And then a 3x squared. Oopsie daisy. 2x cubed minus 3x squared plus 2x plus 1. So it's minus, and then plus 2x plus 1. So that should graph a cubic. I'm not seeing anything over here because my window's weird. So let me zoom out, scroll. Oh, great. Awesome. Okay, so this is why we don't see anything. Our only root is that one irrational value. I hate this already. This is obviously a big screw up. It's cool that I worked really hard on this packet though and tried to make sure that it had no mistakes, right? I think obviously I didn't work very hard on the homeworks. And I didn't. I put all my effort into trying to make sure that the class time examples were clear and made sense. I'm not sure what we do here. Let's just not worry about it. It says no calculator, right? So let's see what we can do without a calculator. And I bet it's going to be a lot. I think that might be the whole point, is that it doesn't matter that we can't factor and do all that other stuff. We're going to know a bunch of stuff anyway. So here's what we know. We definitely know that the domain is still going to be all real numbers, except for the zeros of the denominator. Now hold up. The denominator is x squared plus 1. Isn't x squared plus 1 a parabola that's been shifted up by 1? So just like I was showing you on Desmos, this cubic had only one x-intercept, right? Well, this quadratic has none. So this is an unfactorable quadratic. It has no x-intercepts. That means there's no restrictions on our domain. It's literally all real numbers. There's no vertical asymptotes. So we can do the domain without a calculator. To find the slant asymptote, yeah, we can do that too, because we just know we have to do the polynomial long division. Oh, I did it again. Sorry. I drew a graph that was hidden behind my face. That's the graph I drew. So when I was saying that, that's the graph of x squared plus 1, because you know x squared is a parabola. You know the plus 1 shifts it up 1. That's why we're not getting x-intercepts. That's why we're not getting any vertical asymptotes. That's why our domain is all real numbers with no restrictions, because our denominator will never equal 0. That was the point I was making. Now for the slant asymptote, get rid of this. Boop. And then we'll do the long division and we'll be able to get our answer. So, where's my face? Right here. Let me put a box where my face is so I don't try to write in that space ever again. Alright, what else do I want to do? Let me put a line showing where the bottom of my screen is so I don't write below that line. Boop. That's not a lot of space. Okay, so our long division we're going to take, and I'm going to be just the laziest person ever. I don't feel like rewriting this whole thing. So let me take that bit, boop, and the other bit, and we can do our division. Oh, I can't even do that part because we need a 0 as a placeholder. So I'll be pretty lazy and I'll do just this. So what are we dividing into that? It's going to be an x squared plus a 0x plus 1. We do really need that placeholder. So as we go to divide, x squared is going to go into 2x cubed 2x times. We'll distribute that through to get 2x cubed plus 0 plus 2x. Then you're subtracting. This is canceling. You're getting negative 3x squared. You're subtracting, so these cancel out too. So that's fine. Drop the plus 1. Do it again. X squared goes into this negative 3 times. Technically, we could stop right now. They asked us for the slant asymptote. We got it. It's 2x minus 3. But I got to imagine, yeah, they're gonna ask us follow-up questions. Right here it says, does the function interact? See, I didn't write this packet. It wasn't me. That's not my typo. But whatever. We better keep going because we got to actually find our remainder so that we can figure out if we cross or not. So distribute the negative 3. You get negative 3x squared plus 0 minus 3. I know I'm running out of space. I see myself creeping up on that line. These are going to cancel. And then I find myself adding 3 to 1. I get 4. So we have a constant remainder. That means it'll never equal 0. So if we were to rewrite this, we're going to be 2x minus 3 plus just 4 over x squared plus 1. And that'll never equal 0. So does the function intersect the slant asymptote? No. If so, where? Not applicable. Okay, great. What's the range of this function? I don't know. Not at liberty to say. I feel like I should probably graph a little bit more. What's our y-intercept? That's when you plug in 0. So if you plug in 0, this goes to 0, this goes to 0, this goes to 0, this goes... You see you're just getting 1 over 1. So your y-intercept is y equals 1. Or 0, 1. You want to give it as a y value, I'm fine with that. You want to give it as an ordered pair, I'm fine with that. But we've got a value at 0, 1. You can plot that. We've got our slant asymptote. It's down at negative 3 with a slope of 2. So we rise 2, run 1. Rise 2, run 1. Rise 2, run 1. And then you can connect the dots. Actually, I want more dots, though, to keep it honest. Okay, connect those dots. That's our slant asymptote. And we said our vertical asymptote is that we don't have one anywhere. Oh, I remember this function now, and I hate it. Alright, so I already showed you on Desmos that we did have the 1 x-intercept. It occurred at negative 0.317. I don't know how that helps us. It doesn't. But pretending we did know that, negative 0.3, whatever. There's another point here. I don't know what to tell you guys, but we've got to be asymptotic, right? So I guess our graph is above, because it never crosses. It only crosses the x-intercept in one place. It must come riding along the asymptote. It must kind of deviate from the asymptote to come and pick up these points. But then it must come back down and be asymptotic again. I remember this now. I'm not sure how you would get to this point on your own. But given that our graph follows the end behavior asymptote down forever, follows it up forever, and it has no holes or whatever, it is kind of a foregone conclusion that our range is all reals. That's our shape, that's our thing. So we never had a calculator, but we could do this anyway. Now you turn the page. Boom. Now you can have a calculator. So now what are your zeros? Well, it's that one value. Given that we had a calculator, we could find the coordinates of this point just using the keystrokes on the calculator. I won't ask you to do it because I haven't taught it to you, so don't worry about it. But I know from Desmos that it's negative 0.317. Alright, what's our local or relative maxima or minima? We can go back to Desmos. Boop. Boop. And if we zoom out on the graph, then there appears to be this little bump. But as I click on the red, this function is constantly increasing. So I kind of misrepresented the bump on my graph. Let's graph the 2x plus 3 at the same time. Okay. Okay, 3x plus 2. Oh boy, minus 3? Minus 3. Please be minus 3. Uh-oh. 2x minus 3. That's what I say it is. X squared plus 1. 2, 3, 2, 1. What am I doing wrong? That's the right function. So do I have the wrong slant asymptote? Oh, brother. Can I just, like, stop doing this problem? Alright, let's check our work. And I don't know how to video edit, so I'm going to leave all this crap in. You guys are going to just fast forward through it if you want to, because I don't know how to edit. I do all these in one take. So, sorry. Bear with me. I'm happy with the 2. It's got to be 2. 2x cubed. So 2x, that's right. Then you got negative 3x squared. That would definitely be next. Oh, is that my problem? I never actually put the denominator in. I'm a smart person. Okay, so that's fine. Easily fixed. Alright, kiddos. So you're still seeing the Desmos screen, actually, now that I look. So your teacher, the genius, forgot to actually put in our denominator. X squared plus 1. There. Now, look, everything's back to normal. So I did kind of remember this function correctly. I see that there is that local max right here. There is a local min right here. We've got the y-intercept at 1, like we said. We've got the, we do still have the same thingamabobber, x-intercept. So most of what I said is still true. Let me go ahead and just grab a pic of that. That would be pretty genius. Yoink, yoink. Okay, so now I'll turn this off again. It's supposed to already be off. Okay, I'm back. And here's our graph, which I can't click because I'm clicking on the wrong thing. Ugh. Shrink, move, put on top. So there you can see all the stuff you need. Again, if you're out there thinking, how would I ever do this myself, Mr. F? Well, again, you can use Desmos too. Remember, you're looking at, oopsies, you're looking at the no calculator section. Cut, paste. You're looking at the calculator section. Okay, I'm expecting you to get all these answers from your calculator or from Desmos. So again, the quiz won't be quite like this. The quiz, I'm going to give you the values and you'll go from there. But there's a lot of value in knowing how to use your calculator, knowing how to use Desmos to pull out other values that you need. So I think that's a worthwhile homework task. So anyway, now that you've got this to look at, answering these questions should be cake. What is our local or relative maximum? That's this point. That's the 1.27. Our local minima is this point, and it is at 1. So what's our increasing interval then? We increase from negative infinity all the way up to this local max, which is at 0.296. Then we decrease for just a little bit, and then starting again at 1, we start to increase again. So there's 2 increasing intervals, there's a decreasing interval at 0.296 to 1. And then we can answer these limits. As we go to negative infinity, we're just following that end behavior asymptote, which we can see is taking us down, 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 down to negative infinity. And as we go to the right, we're following the end behavior asymptote the other way, which is taking us up, 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 up to positive infinity. And that's it. So this function that seemed really nasty, well, it is nasty, but the questions that you're asked about it are pretty attainable. Because we don't ask you anything super tough. We don't ask you anything that requires knowledge of the shape of the graph until you're allowed to use your calculator. So it's doable. Alright, that took an extra 15 minutes. So these are long. Obviously these problems just take a little bit of time. Let's do 3. Alright, So 3 is probably factorable. This one is probably pretty similar to what you should expect to actually see on your upcoming assessment. So let's get to factoring. When I multiply, I get negative 40. And factors of 40 that give 3 are 8 and 5. So I've got my 2x. I've got an x. To get an 8, I'll put a 4 here. To get a 5, I'll put a 5 here. To get a positive term in the middle, we want the bigger thing to be positive. So 2 times 4 is the bigger thing, because that's 8. And the 5 will be negative. There, I factored. Uh-oh, x plus 4. Alright, I take it back. This will not be like what you'll see on your assessment. I'm not going to just give you a line with a hole in it. We saw this on the previous homework, though. So it says factor and simplify. We're just getting 2x minus 5, comma, x cannot be negative 4. So we know that our domain is going to be all reals except for the negative 4. The equations of the asymptotes, well, this whole function degraded all the way back down to a linear. So there are no asymptotes of any kind. There's a hole, so there's no vertical asymptote. Sure, here our numerator had the greater degree, so we were thinking maybe there's going to be a slant asymptote. But again, everything canceled. We're not a rational function anymore, so there's not a horizontal or a slant asymptote. POD, that's point of discontinuity, meaning point discontinuity, meaning hole. Everywhere that it says POD, you can just say hole if you want to. We know that the hole has its x-coordinate at negative 4. To find the y-coordinate of it, we plug it negative 4 into the function and solve. So plugging in negative 4 into our simplified function gives me negative 8 minus 5 is negative 13, which is not on the grid. I thought I accounted for all of this, but I didn't. Alright, what are the zeros? Well, the only 0 that counts would be the 0 here, which would be positive 5 over 2. Which is 2.5, so we'll cross the x-axis right there. The y-intercept. You're plugging in 0. We're getting negative 5. Three, 4, 5, so that's here. And we said the hole is at negative 4, negative 13, so 9, 10, 11, 12, 13. So you better just kind of rough that in. There'll be a hole like here, but the rest of the graph will be smooth. And maybe, just maybe, you can hear the gentle whining of my son who's waking up. So I might just stop the whole video here, and you cats have Monday to ask me questions. So if you gotta ask me questions about the rest of 3 and about number 4, you can. But there's a 4, 5, 6, isn't there? 4, 5, 6. So I guess I'll post what I've got so far, so that those of you who want to start looking at it can. And then later tonight, and when I say later tonight, you guys know what I mean. I mean like 9 p.m. 9 p.m. maybe you'll see the rest. Although, little good boy is lying back down. So I'm going to keep talking, actually. What's our range? Our range appears to be all real numbers. But be careful, because we see that there's one y value that we're never going to map onto. And that's the y value associated with the hole. It's the negative 13. So strike that out of the range. And then answering these questions about limits should be cake. As we go to negative infinity, we're just going left, and we see our graph is going down. So that'll be negative infinity. Positive infinity means we're going right, and our graph is taking us up, so that's infinity. As we approach 4, kind of giving away that there's a hole there, aren't we? As we approach from the left, we'll get the negative 13. As we approach from the right, we'll get the negative 13. So the bidirectional limit then is negative 13. But there's everything answered there in the no calculator allowed section. And then in the calculator allowed section, they're asking us for the domain. Oh, this is a whole new problem. I'm sorry. For number 3, it was simple enough that there just was no calculator allowed section, because we could do everything we wanted without it. So we're done with 3, we move on to 4. So 4 is going to be a bit of a pain in the butt. I wonder if any of you remember how to factor differences of cubes. You're going to get x minus 1. Then you're going to get an x squared and an x and a 1. And of course our little mnemonic SOAP is in full form. Our first sign is the same, so because it was a difference, it's a difference. Then you get the opposite sign, so plus. Then you get AP, so always positive, so plus. But this is my numerator factored. In my denominator, this is a difference of squares, so that goes to x minus 1, x plus 1. So the x minus 1's cancel. That indicates right away that we do have a whole, and that the x coordinate of the whole is going to be 1. That also tells me that in my domain, it's going to be all real numbers except negative 1 and 1. Negative 1 is going to be a vertical asymptote, though, and 1 is going to be the whole. So we have a vertical asymptote at x equals negative 1. We have a whole at x equals positive 1. Slant asymptote, yes, it does look like we'll still have one of those, because even after canceling, we do have a denominator, and it's 1 degree less than the numerator. So we'll have one of those. Long division will give us its equation. For our y-intercept, we're still just plugging in 0. And you can see when you plug in 0, you get negative 1 over negative 1, which is 1. So the y-intercept is 0, 1. Yeah, 0, 1. So that's a lot. That's a lot of stuff right there. In terms of factoring and simplifying, we get the quadratic. In terms of quotient plus remainder over divisor form, we got to do our long division. So let's do that. Where's my pen? Right here. So I should not go below this line, or you guys won't be able to see what I'm doing. Alright, I got plenty of room up here though. So we're going to do x plus 1 into x squared plus x plus 1. So x goes in, x squared plus x. Uh-oh, trouble. That means when we subtract, this cancels, this also cancels. So there's no other term in our quotient, and that's fine. Our slant asymptote could just be y equals x. Our remainder then is just the 1. So our quotient plus remainder over divisor form is just kind of simple. It's going to be x plus 1 over x plus 1. That's our form. So that means we can sketch in that slant asymptote then. It's just going to be that and this. We have a vertical asymptote at negative 1, so we'll sketch that in too. We've got a hole at 1. And when you plug in 1 to our simplified function, you get 1 plus 1 plus 1 for 3. 1 plus 1 is 2, so 3 over 2 is 1.5. So at 1, 1.5, we're going to have our hole. It says, does the function intersect the slant asymptote? Still no, because our remainder over divisor is back to having a constant in the numerator, so it will never equal 0, so it will never cross. So this is a no. If so, where? Not applicable. Okay, so I'm pretty satisfied then that if we've got the hole right here, we can sketch this entire branch. It's going to come down, 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 turn. I didn't plot the y-intercept, did I? So I could do this a little bit better. Since our y-intercept is here, then now we know we're going to come down, pass through there, come up and out. Now, is the y-intercept also our local min? I tend to think it probably isn't. We would go to Desmos, though, to find that out for sure. But I bet that's not the minimum. I bet the minimum is somewhere between the y-intercept and the hole. Or maybe it's on the other side. I'm not sure, honestly. So what about the other side? I guess we better run a test point to be sure. I'm partial to negative 3. So negative 3 on the line y equals x has a y value of negative 3. So we're testing against that. Plugging into maybe the original is the easier one to evaluate. Actually, it has just a few terms. So negative 3 cubed is negative 27. Take away 1 is negative 28. And then positive 9 take away 1 is 8. So is that less than negative 3? Yeah, it is, because 8 times negative 3 is 24. So negative 28 would be slightly further down. So we're going to be here-ish. So that means we'll come up, up, up along this asymptote, hit that, achieve some max, come back down. This is a rough sketch, but I'm happy with it. So what's our slant asymptote? Y equals x. So I've answered every property of sketch the graph. So on the next page, they're probably going to want more information from us. So again, we'll go to the calculator. So cubed, squared, minus, minus. Alright. So there's your numerator. There's your denominator. There's our function. Our slant asymptote is just x. So we could sketch that in if we want to. I mean, if you really want to, you can sketch the vertical asymptote in too. You just say x equals, what was it, -1? That looks right. And if you really wanted to, you could hit the cog. See the little cog up here? And you can change the color of this to, you know, red and dashed. This could be red and dashed, and then the original function can be blue or something. So there you go. Now, did we have a hole? Yeah, we're supposed to have a hole at -1, right? Maybe I don't know what I'm talking about. +1. Where's our hole? One comma 3/2. Okay, so again, if you were into this, you could actually plot a point at 1 comma 3/2. Oops. And then that'll actually show you the dot. And if you are super into this, then you click the cog, click the dot here, and you can make it an empty circle. And you can make it blue too. But there you go. Now we've got an actual really good looking graph. I can click the graph, I can find that max. Ooh, look at those points, they're so clean. That doesn't usually happen. I don't know why this is doing this to me, but it's bothering me quite a bit. Okay, so I'm going to just grab a picture of that, and then we can answer all the follow-up questions. Turn this off. Okay, I'm back. So there's our graph. So now as they ask us for the range, it's a nice and easy one because the local maxes and mins are such nice clean values. So our range would be -infinity up to -3. Hard bracket. Union, 1 to infinity. Now they want the relative max. The relative max is this guy, so it's y equals 1. The relative min is this guy down here, so -3. Increasing intervals should be cake. We're going to increase from -infinity up to this point, which is at -2. Then we decrease to the asymptote, and beyond the asymptote we're still decreasing, but starting here at 0 we start to increase again, so 0 to infinity. So the decreasing intervals then would start right here at the 2, go to the asymptote at -1, then start again from -1 and go up to this extrema, which is at 0. So that's how those fit together. Our limits again should be a piece of cake. Our left hand limit is going to take us down to -infinity. Right hand takes us up to +infinity. -1 is what? Our vertical asymptote. So as I approach from the left, I'll be headed down to -infinity. As I approach from the right, I'll be headed up to +infinity. So the bidirectional limit does not exist. And at 1 we have the hole. So as I approach from the left, I get 1. As I approach from the right, I get 1. And the bidirectional limit gives me 1. So there's everything. Once you're allowed to use a calculator to find those extrema, once you're allowed to look at the graph, answering all those questions shouldn't be too bad. Let's go to 5. Alright, looks like we're on our own for factoring again. So looking at the numerator, I'm going to need to put a 3 right here and a 1 right here. That gives me an outer product of 2 and an inner product of 3. I want the 3 to be negative, the 1 to be positive. There, I factored. Now this one is going to be, so it's negative 6, so negative 2, negative 3. So it'll be x minus 3 and x minus 2. So this is my factored and simplified form. Boop. My domain is all reals, except for those two denominator values, 2 and 3. Are vertical asymptotes. They're both vertical asymptotes. So x equals 2, x equals 3. Horizontal asymptote, we've got those same degrees, 2 and 2. So you take the leading coefficients, which is 2 over 1. So your horizontal asymptote's at y equals 2. For zeros, you just take the zeros of the numerator, so negative 1 and positive 3 halves. For a y-intercept, you're plugging in 0. All these terms cancel, except for the constants on the end, so that gives you positive a half. Just a regular parenthesis there. Does the function intersect the horizontal asymptote? How do you figure that out? I think we said that you need to take the entire function, ideally in its expanded form, and set it equal to the y value of the horizontal asymptote. So we're going to take 2x squared minus x minus 3 all over x squared minus x minus 6, and we're going to just set it equal to 2, and we're going to try to solve. So we get a 2x squared minus x minus 3 equals 2x squared minus 2x minus 12. So right away I see that if I subtract 2x squared from both sides, they cancel. If I add 2x to both sides, then I'll get a positive x here. Then to isolate, I'll add 3 and I'll get negative 9. So does the function intersect? Yes. If so, where? At x equals negative 9. Alright, so start plotting. I'm going to cheat just a little. Vertical asymptote at 2. That's here. And then there's another one so soon, right at 3. Then our slant asymptote. No, we don't have one of those. We have a horizontal at y equals 2. So that's here. Alright, there's your asymptotes. Now we plot other points. So the zeros are at negative 1. So there's an x-intercept there. 3 halves is 1.5. That's here. I don't like that one bit. And the y-intercept is a half. Are you sure? Alright, I'm a fool, as usual. But I figured it out. I wonder how long you guys were screaming at the screen, saying I'm a big dummy. I hope you are. These are not both negative. This is supposed to be positive. So that actually means one of our vertical asymptotes is at negative 2. That means negative 2 is getting removed from our domain. I don't think it changes anything else though, except for our graph. Which means I should be able to move that line. It's hard to move these lines. Just delete it. Do it again. Excuse me, that feels a lot better. So now, we know that these 3 points here, those pretty well define our graph in this interval. It's just going to be sort of a downward opening, concave down U-shaped thing. The intersection with the asymptote at -9 is helpful, but again, I don't know whether I'm above it or below it. Would have to do some math to figure it out. But let's play this game as if it was the quiz. I would be handing you the critical points, right? So let me go find those critical points, and then we can kind of go from there as if we had been given them from the get-go. Okay. So here's those points. For one of them is completely useless to us, on our grid at least. But we do have this other one. So the 165,507 or whatever, that's like just right next to our y-intercept. So that kind of doesn't help us either. We kind of already knew that we were going to come running up, 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 hit through those points, go back down. We already knew that. So having that one point doesn't really help us shape our graph. We already knew it was going to be that way. The other one though is way out here, and it's a little less than 2. So that at least does tell us that our graph is doing one of these. It's going to be coming down this asymptote from above, hitting at the point of intersection, and then way, way, way out here at like -18, it finally hits a minimum, comes back up, and approaches the asymptote from below. Again, I'm exaggerating that. I'm exaggerating that a lot. I think we're going to have another gap here. When it asks us for the range, we'll have to address that gap. Yeah, I mean, for sure we have a gap, because this thing only comes as high as about 0.5, and this thing only comes as low as about 1.9. So we're going to have that gap again. So you know what? Let me graph this more to scale. We come down, we hit here, and it basically feels like you're already riding along the asymptote. You almost can't see a dip at all. It just feels pretty horizontal. But the numbers tell us that there's a dip, so trust it. On the other side, we have to run test values. So plugging in 6. I'm not just checking if I'm positive or negative. I have to actually check to see if I'm greater than 2 or less than 2. So you kind of have to do the math a little more for real. So if I check x equals 6, I'm going to use the factored form, I guess. So 12 minus 3 is 9. 6 plus 1 is 7. 6 minus 3 is 3. And 6 plus 2 is 8. So I can kill this. That's a factor of 3. I'm getting 21 over 8. I just want to be more than 2. And this is more than 16. 16 over 8 would be 2. So 21 over 8 is more than 2 for sure. But less than 3. So I'm somewhere between these values. And then I can draw the rest of my branch. It's just going to come down, pass through that point, and be asymptotic. So there you go. So there's that graph. And there's all the questions answered. So let's just do the next part. And then I gotta go because my son's waking up again. Quiet, Luca. Okay, there's our graph. So again, as long as you guys have a picture to look at, then I think this should all be easy. What's our range? I already warned you. We're going to have that one little void zone in the middle here, but it's going to be -infinity up to this local max, which is 507. I'm going to call it 0.507. I could be misreading it, but I don't think so. Then the graph picks up again at this local min, 1.973. And from there it goes up to infinity. So that's our range. Our local relative max would just be this guy. You given the y value, so 0.507. And our local or relative min is the y value way over here, so the 1.973. Increasing intervals. So at first I'm decreasing until I get to this critical value. Then I'm increasing, so I guess I'm increasing from -18.165. So from there I increase all the way to the asymptote at -2. Then from there I continue to increase until I get to this local max, which is at 0.165. Then it decreases forever. So just the two increasing intervals. Decreasing intervals would go from -infinity all the way up to the 18.165. And then that goes up to, yeah, then we're increasing till we get to the asymptote. Then we increase to the local max. So we're going to be increasing again starting at the local max of 0.165. I'm saying decreasing. We're going to be decreasing from 0.165 to the next asymptote, which is at 3. Then we decrease again from 3 to infinity. So that's that. And then for our limits, the end behavior limit is our horizontal asymptote at 2. So as I go left, I approach 2. As I go right, I approach 2. -2 is this asymptote, which from the right has me going up to infinity, but from the super psych. From the right, it has me going down to -infinity, right? From the left, it has me going up to +infinity. And lastly, at 3, it's the same deal. From the left, I'm going down. From the right, I'm going up, which means the bidirectional limit is, it does not exist. Alright, it's been an hour and a minute. So sure, there is another question called number 6. Do it yourself. Do it yourself. Ask me on Monday. Good luck, kids. Enjoy. I'll see you later. Bye.